Welcome to this presentation, which will be about adaptive security policies via belief aggregation and rollout. So we consider a networked system that consists of a set of interconnected components, some of which may be compromised by an attacker. And the problem is to find an effective security policy that uses measurements from the system to prescribe security controls, such as flow control or access control. Conceptually, you can think about this problem as a POMDP, where we have a system state X, we have an observation Z, and we have a control U. And the problem is to find a security policy mu that minimizes the expected cost. And this cost can be interpreted via the following graph, where on the x-axis you have time and on the y-axis you have system performance. And at some unknown point in time, indicated by the left dotted line, an attack event may occur. And when this happens, we want that the system maintains some acceptable level of performance and as quickly as possible recovers to normal performance again. And while this problem can be formulated as a regular finite POMDP, it has a few characteristics that makes it very challenging and also quite interesting. And the first characteristic is the sheer scale of the problem, where these type of systems typically consist of many components, each of which can be in different states and have different controls. And therefore, we run into this combinatorial explosion where the complexity of the problem grows exponentially with the number of components. The second major challenge is that the type of systems that we consider are changing all the time in unpredictable ways. So components fail, bandwidth fluctuates, load patterns shift, software is updated, new vulnerabilities are discovered, and so on. And this means that the problem of finding an effective security policy is not a problem that can be solved purely offline. Rather, we also require some online mechanism so that we can adapt the policy to changes when they occur. And our main contribution is a general framework for approximating POMDPs that enables this type of adaptation. And this framework can be understood on a high level through the following picture. And it comprises three main parts. So first, we have an offline part down here, where we optimize a base policy by using dynamic programming in an aggregate belief space. And then we have an online part, where at each control cycle, we estimate a belief of the system state, and then we use that belief to adapt the base policy via rollout and lookahead optimization. And we show experimentally that this framework achieves state-of-the-art performance on a standard benchmark. And moreover, it has quite appealing theoretical properties, especially when you compare it to other approximation frameworks like deep reinforcement learning, for example. So in the rest of this talk, I will go into all of the details about this framework, both the theoretical aspects and also the experimental evaluation. The starting point to understand our framework is the classical belief space formulation of POMDP, where the insight is that the conditional probability of the current state is a sufficient statistic for control. And therefore, if we define the belief to be our state, we obtain a perfect information problem in belief space. And since this space is compact, all of the dynamic programming principles and operators apply. So this simplifies the problem quite a lot conceptually. Computationally, however, we still have many challenges, and chief among them is that the problem is p-space hard, regardless if we use the belief formulation or the original formulation. The second challenge that we encounter when we are in this large-scale regime is that the dimension of the belief space is so large that we cannot even enumerate one of these vectors. So in our framework, we tackle these computational challenges via problem simplification, where we take the original problem and then we simplify it using aggregation. Then we solve the simplified problem using dynamic programming. And then we use that solution to approximate the original problem via interpolation. So more specifically, the way that we simplify the problem is by using a two-level aggregation, where we first aggregate the state space into a smaller feature space. And this feature space should be small enough so that we can construct beliefs over it. And then we aggregate those beliefs into a finite subset called Q tilde. And Q tilde then defines an aggregate problem that can be solved using dynamic programming. So the first step in carrying out this aggregation is to define the feature space. And there are two principal ways of doing this. Either you can define it manually based on engineering intuition or domain knowledge, or you can do it automatically via a neural network. And which approach is most suitable really depends on your specific problem. Once we have constructed the features, the next step is to map each feature to a subset of the state space. So this should be the subset of states that are most related to that particular feature via some similarity. And this then allows us to do a one-to-one mapping between each of those subsets to the corresponding feature. And to also be able to map states that are outside of those subsets, we then introduce a state aggregation probability distribution called phi. And that allows us to take any point in the state space X and generate the corresponding feature. And to go in the opposite direction, we also introduce a disaggregation probability distribution called D that allows us to take any feature and then disaggregate that into a state. So in total, we now have three possible transitions. We can transition within the state space using the regular kernel. We can transition from a state to a feature using the aggregation probability. And we can transition from a feature back to a state using a disaggregation probability. So effectively, we end up with a dynamic system with the following transition diagram. So in the bottom, we have the feature space. We can go up to the state space, we can go across, and we can go down again. And this means that we now have a well-defined aggregate problem in feature space, where we can start out with some feature, select some control, then we generate some cost and a subsequent feature. And then we can continue propagate it forward like this. And one can show that this aggregate problem has a well-defined Bellman equation, and it can be solved using dynamic programming. However, to solve this problem, we need to be able to observe the features. And that is typically not possible in a POM-DP. So now the next or final step of the aggregation is to lift this whole structure to the belief space instead. And we do that in two steps. So first, we take the original belief space B and we map that to the feature belief space, which has a smaller dimension. And this mapping is actually already implicitly defined by the feature aggregation. So we already have that mapping. And then we aggregate the feature belief space into a finite subset called Q tilde. And this aggregation is defined via a belief aggregation probability that we denote with psi. So psi allows us to take any points in Q and then generate the corresponding Q tilde. And naturally, you want psi here to encode some similarity between your beliefs. So a common choice, for example, is that you define psi based on the nearest neighbor mapping. And in that case, you effectively partition Q into these Voronoi cells, where each cell contains the beliefs that share the same nearest neighbor. And this is a special case of what we call hard aggregation. But you can also define soft aggregation by using a more general definition of psi. So what we end up with now is a dynamic belief system where we can go from the original beliefs to the to the feature beliefs, and then we can go to the aggregate beliefs in Q tilde. And just like we had a well-defined aggregate problem in feature space, we now have a well-defined aggregate problem in the feature belief space Q tilde that can be solved using dynamic programming. And then we can use the solution to that problem to approximate the original POM-DP. So more specifically, the way that we do this approximation is that we first define V star to be the optimal cost in the aggregate problem. And then we approximate the original POM-DP via the following interpolation formula. And that gives us J tilde, which is the approximate cost. And once we have J tilde, then we can also define a base policy for the POM-DP. And there are many ways you can do this, but one approach would be to define it via a Bellman equation like this. Also, if you have hard aggregation, then you don't even need to use a Bellman equation. You can just directly get the policy from the optimal policy in the aggregate problem. So that is how we approximate the POM-DP offline. But now the big question is, of course, how good is this approximation? So in other words, how close is J tilde going to be to J star? So what is the approximation error? And to understand this error, you can consider the following picture, where when we have hard aggregation, then for each Q tilde in the capital Q tilde, there is a corresponding set in the original belief space that we call the footprint set. I denoted here with orange circle. And the error of the approximation is then determined by how much J star varies within that subset. So if J star doesn't vary that much, then we have a good approximation. If it varies a lot, then we will have a poor approximation. And if it is constant, then we can actually have an exact optimal solution. So this is formally expressed by the following proposition. And this also gives us some insight into how we want to design the features of our problem. So we would like that states that have similar cost also have similar features, because that will then lead to epsilon being relatively small. And here's an experimental illustration of this bound, where I applied the approximation to a small POM-DP with only 2 states, so that I can visualize the cost. And on the x-axis, you can see the belief, and on the y-axis, you have the cost. The solid black curve shows the optimal cost, and the two other curves are approximations. So what we can see is that the approximations have the same general structure as the optimal cost, but they are lower bounds to the optimal cost. We also note that the size of the aggregate feature belief space, Q tilde, affects the quality of the approximation. So the larger this set is, the better approximation you can expect. And this is of course not surprising because if you look at the figure here, then the larger Q tilde you will have, the smaller those orange footprint sets will be in general, and therefore epsilon will generally also be smaller. And by the proposition, you will then expect a better approximation. But of course, there's a trade-off here because when you increase Q tilde, you also increase the computational complexity of your aggregate problem. So if you now look at the bigger picture, what we have covered so far is a general aggregation framework for offline approximation of the POMDP. And this is a scalable approximation in the sense that we can adjust the computational complexity based on the available compute resources by tuning the number of features and the resolution of the aggregation. And this offline optimization then gives us a base policy and an approximate cost, J tilde. And now the second part of our framework is about how we can refine that base policy online. And the way we do that, as I mentioned earlier, is via two steps. So first, we estimate a belief of the system state using a particle filter. And then we use that belief to adapt the base policy using rollout and lookahead optimization. Now, the reason why we use a particle filter is simply because this type of systems that we consider are so large that it is intractable to compute the exact belief. So we instead estimate it with a particle filter. And this is relatively straightforward. So we maintain a set of sample states that we call particles. And those particles induce a probability distribution over the state space. And that distribution is then our estimated belief. And a nice thing about this filter is that the complexity can be controlled by setting the number of particles. And it also is consistent in the sense that when you increase the number of particles, you can expect a better estimation. And once we have estimated the belief, this then gives us the starting point for the look-ahead optimization, where we start out in some belief, then we look forward a few time steps, 2 in this example, and then we end up with a bunch of future beliefs. And from all of those beliefs, we then do rollout with the base policy for m time steps into the future. And then we use a terminal cost approximation provided by J tilde. So just to remind you, both the base policy and J tilde is what we obtain from the offline optimization with the aggregation. And once we have done this look ahead and rollout, we then do a minimization where we select the control that leads to the minimal cost according to our look ahead calculations. And here is exactly what I just said, but in terms of two equations instead. So the look ahead optimization can be expressed with a standard Bellman equation, where L is the number of look ahead, it's basically look ahead horizon, and alpha is a discount factor. And similarly, rollout can be expressed mathematically as a Monte Carlo evaluation of the base policy with a terminal cost approximation provided by J tilde. And here L is the number of rollouts, so the number of samples you use for the evaluation. Now, the benefit of doing all of these extra calculations online is that the policy that we obtain, the rollout policy, mu tilde, is guaranteed to improve the base policy under general conditions. And moreover, its suboptimality can be bounded by the following inequality, which is very well known. And here is an experimental illustration of these bounds for a very small POMDP, just to give you the general idea. So this is the type of result you always get when you do rollout, where on the y-axis you have cost and on the x-axis you have different aggregations. So you see that the rollout policy will always give you an improvement compared to the base policy. And sometimes this improvement can be quite small, but in other cases it can be very dramatic. And there's actually a very interesting theory underlying this, developed by Bertschekkas, where there's a connection between the minimization in the rollout and one step of Newton's method. So when the base policy is sufficiently close to optimal, then just as Newton's method, you can expect superlinear or quadratic convergence to the optimal policy. And that can explain why we sometimes see this dramatic improvement. So that concludes or completes the whole framework. And just to summarize it, so this is a scalable framework for approximating POM-DPs. And it's scalable in the sense that the computational complexity can be adjusted to your available compute resources. So you can tune the number of particles, you can tune the resolution of your aggregation, and you can control how many lookahead steps you're going to do. And the framework has quite appealing theoretical properties, where the particle filter is consistent, the aggregation error is bounded, and the improvement of rollout is guaranteed in general. And now I'll move on to the experimental evaluation of this framework. And to evaluate the framework, we apply it to a standard benchmark problem or benchmark POM-DP called Cage2. And currently there's something like 35 different methods that have been evaluated against Cage2. And right now, the state of the art is based on deep reinforcement learning, or different variants of PPO in particular. To instantiate our framework for this benchmark, we first define some features of the problem based on some intuition. And then we define a aggregate feature belief space with around 500,000 beliefs. This gives us a well-defined aggregate problem, which we then solve using dynamic programming or value iteration in particular. And that gives us the base policy and the approximate cost J tilde. And then for the online adaption, we do 2 lookahead steps with 50 particles. And here are then the results. So the first column indicates the method, the second column indicates the compute time, the third column indicates the state estimation. So the current deep reinforcement learning methods do not maintain any belief, and they just use the latest observation as input to their neural network. But to enable a fair comparison with our method, I also evaluated them with the particle filter as input. And the final column, the fourth one, shows the cost. So if you start from the top, we have the base policy mu. Then we have 3 deep reinforcement learning baselines, PPO, PPG, and DQN. And then we have the current state of the art, or the previous state of the art, called Cardiff, which is a deep reinforcement learning method based on PPO that was specifically designed for Cage2. So it is basically PPO with certain heuristics. And then we have POM-CP, which is a Monte Carlo tree search method for POM-DPs. And finally, we have our framework with 3 different rollout horizons. So 0, 10, and 20. And what we can observe is that our framework in combination with Cardiff achieves the state-of-the-art performance. So both of these 2 methods are statistically equivalent in terms of performance. But we can also note that our method is significantly more efficient than Cardiff. So Cardiff requires around 300 minutes of offline computations on my server to get good results, whereas our framework requires only about 8.5 minutes. So it's a big improvement there. And another surprising result here is that the base policy that you see on the top is surprisingly good. And it's actually very close to state of the art with just the base policy without any look ahead. So this was the evaluation for cage 2 when the system remained stationary throughout the entire evaluation. But we also did an evaluation where the system changes in unpredictable ways, which is a bit more realistic. And in that case, we can see that the offline methods, such as the base policy and the Cardiff, performs quite bad. Whereas our method, which is able to adapt to the changes, gets a significant improvement in terms of cost. And notably, this improvement is also very significant when you compare it to the other online method, namely POMCP. So in conclusion, we have presented a scalable framework for approximating very large POMDPs, which has theoretical performance guarantees and achieves state-of-the-art performance on a standard benchmark. And it comprises three main parts: offline policy optimization using dynamic programming in an aggregate belief space, online policy adaptation using rollout and lookahead optimization, and online belief estimation via particle filtering. Thank you very much for your attention.